Today we're going to talk about finding real basic limits. So we're going to start, and actually all we're going to do today is talk about limits for functions that are continuous on their entire domain. So if a function is continuous on its entire domain, meaning it doesn't have any breaks in it whatsoever, you can draw it without picking up your pencil. Then at every domain value, except possibly the endpoints of the domain, then the limit as x approaches a of f of x equals f of a. So really all this is saying to us is if a function is continuous at a for some interval surrounding a, then its limit is just the value of the function. So if we look at a function or a limit here, like the limit as x approaches 4 of 2x minus 3, the first thing we want to think about is 4 in the domain of this function? And the answer to that is yes, 4 is in the domain of 2x minus 3. And then second thing we'll think about is 2x minus 3 a continuous function? The answer to that is yeah, it's linear, right? It's continuous for all real numbers. Therefore, the limit as x approaches 4 of 2x minus 3 is just the value of the function at x equals 4. So in this case, that's 2 times 4 minus 3, which is just 5. Pretty straightforward. We'll go through the same general thought process for the next one. The limit as x approaches negative 3 of x squared plus 1, where we'll think, is negative 3 in the domain of x squared plus 1? Can we square negative 3 and then add 1 to it? And the answer is yes. And is x squared plus 1 continuous? The answer to that is also yes. It's a parabola, and parabolas are continuous for all real numbers. Polynomial functions in general are continuous for all real numbers. And so all we have to do is evaluate the function x squared plus 1 at negative 3. So we'll do negative 3 squared plus 1, which will give us 10. And then for the last one we've got here, we've got the limit as x approaches 2 of the square root of the quantity x plus 7. So we'll, again, go through that same process. Is this function defined at x equals 2? And the answer is yes. You can plug 2 into that. You can do 2 plus 7, which is a positive number, and square root it. You can square root positive, right? So that's fine. And then we'll ask ourselves, is this function continuous for its entire domain? And the answer again to that is yes, right? This thing's domain is negative 7 to infinity, right? Using our interval notation there, the domain of this is negative 7 to infinity, because if I have anything below negative 7, like negative 8, we end up with the square root of a negative, which we can't have. And at negative 7, we get the square root of 0, which we can do, and anything above negative 7 is positive inside the radical, and so we can do that as well. So since this is continuous on its domain, right? Radical functions are continuous on their domain, right? Then all we have to do is plug in 2. This just becomes the square root of 2 plus 7, square root of 9, which is 3. And a lot of times the question comes up as well can't it be negative 3 also? The answer is no. This is the positive square root. If it had a negative sign in front of it, then the answer would be negative 3. But we don't have that in front of it. This is the principal or the positive square root of x plus 7, so our answer is just 3. The next thing you're going to want to remember about limits is that the limit of a constant is the constant. In other words, the limit as x approaches a of c, some real number constant, is just c. And if we think back to our previous rule that we just had, this just is a basic application of this rule, right? Let's say the function was y equals 12. Well, 12 is a function that is continuous on its domain. It's just a straight horizontal line. And therefore, the limit as x approaches any a value of that horizontal line should just be the value of the horizontal line. Right? So we're thinking about this as if this is the function y equals 5, right? Y equals 5 is continuous. And so the limit should just be the value of the function at any given x value, because this is continuous for all real numbers. Therefore, as we approach 3, the limit of 5 is if I said what's the limit as x approaches 7 of 5, the answer would still be 5. If I said what's the limit as x approaches negative 1,000 of 5, the answer would just be 5. And likewise over here, negative 32 is just a constant function. The limit as x approaches 6 of negative 32 is just negative 32. It's just the constant. So we'll do one more quick set of these, and then we'll be done for today. Pretty straightforward little lesson here today. So first we'll look at our function f of x equals x squared plus 5x minus 3. And if we think about that function, it's just a parabolic function. It's a polynomial function. Polynomial functions are continuous for all real numbers. And so each of these limits that we're looking for should just be the value of the function evaluated at the different a values. So we've got 0 squared plus 5 times 0 minus 3, or 0 plus 0 minus 3, which is just negative 3. Here we've got the limit as x approaches 3. So that'll just be 3 squared plus 5 times 3 minus 3. And that would be 9 plus 15. 9 plus 15 is 24. And then we'll subtract 3 from that to get 21. And for this last one, same function, still a continuous function. So we'll just plug in negative 2. We've got negative 2 squared plus 5 times negative 2 minus 3. And so negative 2 squared is 4. And then we've got 4 minus 10 is negative 6. And negative 6 minus 3 is negative 9. And I'm not 100% sure why we got these little dots over the x's. Those shouldn't be there. Those don't mean anything to us here. In this case, those are just accidentally there, a little typo. And that's all we're going to do today. The two important things to remember are that the limit of a constant is the constant, and that if a function is continuous on its domain, then at any domain value, the limit as we approach that a value is just the function evaluated at a. And next time we're going to get into what happens when our function is not continuous at a. That's what actually starts to make limits a little bit more difficult. Everything so far has been pretty straightforward with finding these limits. But as soon as we are looking at what happens as we approach a value that doesn't exist for our function, it's going to get more complicated. So we'll take a look at that next time. And that is going to be it for today.